third example that we will study, to move away a little bit from physics, we will study in biology Darwin's natural selection. So the phenomenon now is completely different, it's not a physical phenomenon, is why so many different species exist. We have giraffes, monkeys, birds, reptiles, trees, we have all these living beings in the world, and we need an explanation why this and why not others. We also know that there have been some other species that are not here anymore. And we know that also that we change, there might be changes in time in the future. We might predict this or expect this. So the question is, how do we approach this? Did God make this? Is there a fundamental principle, or it is because we receive the animals from other planets and they come in asteroids or something, or in ships, or aliens bring them here? We need an explanation. So the scientific thinking will try to find a reduced number of variables and a simplification principle to explain this. And this is the genius of Darwin, indeed, in relation to this theory of natural selection. So the first idea is to think a species in terms of nothing but a population that lives in a place. A species, let's say a dog, is a population in a specific place. In another place will have another population, in another place another population, and so on. So all animals, all species more generally, can be described as populations in specific places. And now, very simple idea is that the population of a species in time will depend in its ability to reproduce in the conditions of such place. If the conditions are good, it will be able to reproduce. If the conditions are bad, it won't be able to reproduce as much, so maybe in the long run will not be there anymore. The other important principle is that new generations of the certain species inherit most of the features of its predecessors. But some features might also change from generation to generation. So that's what we see, for example, with ourselves in relation with our parents. We inherit several of their features, but some of them also change. So if we look at this in a long run, we can see that there might be major changes, even though the changes from generation to generation are small. And now the question is, how these changes are going to happen? What are the changes that we will see in the long run? And this is the genius of Darwin, is to say, the novel features in this long way of changes, the novel features that will become part of our reality are those that have increased the chance of reproduction of the generation path, which is called a lineage. Lineage is the generation's path of a certain species. And eventually these lineages change. You look at a certain part in the future with respect to the past, and it might be very different. Because from generation to generation, there have been little changes which cannot be even maybe noticed. But in the long run, little plus little plus little plus little, you get a big change. So that is what eventually might create variations of different species. They can start from something very simple and start becoming more different. And the thing is that lineages then evolve adapting to their environment. And that's the simple idea of natural selection. We don't need to think of the size, of the weight, of the intelligence, of the whatever physical features of the species to explain that. With this very general principle, we encompass the evolution of all the species in the planet. Of course, then we can go and be more detailed and look at the particular evolution of certain group of monkeys into other monkeys and get into the human, or look at the reptiles or the birds and so on. In the same way, for the theory of gases, we can look at the specific forms of gases at the specific temperature ranges, or try to look for cycles of changes of variables and so on to describe and create descriptions, more refined descriptions. Same with mechanics, we can look at projectile or circular motion or linear motion. We can make more specifications about what we want to study, but the general principle, which is the most important to have a description of what we want to explain, of the phenomena, will not change. So that's the idea of reducing and simplifying phenomena. That's what has been done in pretty much in all science, traditional science, let's say. So the very little summary, you can look at astronomy. The entity is described by the mass, the position, the speed, and the acceleration. The interaction on which things depend is the gravitational force, and the simplification is the Newton's law. Then the gas theory, you get temperature, pressure, volume, and number of particles. The interaction is heat exchange, and then the simplification is maximum entropy, which you don't need to know these details, but these are just facts. Like, you can take them as facts. There is a simplification principle, there is an interaction, and this entity is described in a very simple way. For natural selection, we get that the entity is a population in a specific place. And the population is actually described as a collection of traits, so features. The interaction is adaptation to the environment, and the simplification principle for explaining natural selection is the reproductive success. More successful species, species that are more successful at reproducing will be better adapted and thus will remain in time in the specific region. So its population is going to grow or maintain. So with this very simple way to describe an entity, an interaction, and a simplification principle, we get most of the science. So I give you this very simple example, exercise. I suggest that you try to develop the same table for other areas of science. I give some examples of these areas of science here, but you can choose any other you want, and explain how entities are described in chemistry or in optics, what types of interactions are necessary to describe the chemical, for example, a phenomenon, and what is the simplification that makes things easier. In all these phenomena you can write this. Maybe you might need more than one simplification or more than one interaction, but never more than 2 or 3. It's always reducible to something you can write. And that's the very important aspect of traditional science, that all the reasoning you can do about it is very easy to describe in few words. We're going to see that for complex systems, it's not always the case. See you in the next video.